Good evening. Hello, thank you so much for coming to SoundWaves. Great to be back in person, and it's nice to see all of you here. End of winter presentation of SoundWaves, and today we are tackling questions of size and scale with 4 brilliant presenters and 1 brilliant musician. And I think without further ado, we'll just get started.
Okay, well, let me introduce myself. My name is Brian Rabel. I am a professor in the physics department, and I'm going to tell you about neutrinos, which are some of the smallest particles in the universe that we know about, but I hope to convince you by the end of this talk that they are extremely big deals. So let's get started just kind of with a little context and give you an idea of what neutrinos are. So there are 12 fundamental particles that we know about. These are particles that are not made up of anything else. They are just as small as you can get and as fundamental as you can get. They are what they are. They're not something else smaller behind them. And so let's talk about them for a few seconds. In the upper left here, as you're looking at the screen, we have the quarks. There's 6 of the quarks. Now, what the quarks are for the purposes of this talk aren't really all that important, but you should maybe pay attention to the first two there all the way over on the left, the up and the down. Those quarks in certain combinations will make protons or neutrons. And so those are what makes up the nucleus of atoms, and in turn will make up you and me and everything that we see in the universe around us. Now there's 6 other particles that come in another family that we call the leptons, and those are on the lower left. The leptons are divided into 2 types of particles. There's the charged ones. They carry some kind of electric charge. And so the one you're most familiar with from your chemistry classes or physics classes that you may have had in high school or college is the electron. That's a lepton. The other 2, the muon and the tau, are basically progressively heavier electrons. You can think of them in those terms. Now the other 3 leptons are the neutrinos, and that's what we're going to talk about for the next few minutes. And these neutrinos, they're always paired with one of the charged leptons. So you have an electron neutrino, a muon neutrino, and a tau neutrino. And if you do the math quickly, what you'll notice is that neutrinos are a quarter of the total fundamental particles, the quarks and the leptons. And so that by itself makes neutrinos interesting to study, because they're 25% of the particles that aren't made up of anything else in the universe. They also are interesting because they have no electric charge. They're completely electrically neutral. An electron has a negative electric charge, so does a muon and a tau. A neutrino has 0 charge. And what that means is that neutrinos hardly notice any other type of matter. They can just pass through everything. So if you stuck a neutrino in front of a light year of lead, so that's a piece of lead that is 1 light year long, or the distance that it takes light to travel in 1 year, it will just pop out the other side. And that's why we call it, a lot of people have called it over the years, the ghost particle. It basically walks through walls. It just goes through anything and it doesn't care. So let's see where neutrinos come from. So we can start way back at the beginning of time, the Big Bang. And neutrinos were produced in the Big Bang. There's 357 neutrinos that were produced in the Big Bang in every cubic centimeter of the universe today, almost 14 billion years later. That's pretty amazing to think about. At the beginning of time, these neutrinos were produced. 14 billion years later, you can take your thumb, which is about 1 cubic centimeter, the tip of your thumb, put it anywhere you like, anywhere in the universe, and there's 357 of those neutrinos still around. That's kind of incredible to think about, that they've just been there for 14 billion years. Now, they also played a big role in the development of our universe. It turns out that neutrinos helped encourage the formation of galaxies in our early universe. The fact that they were there and they added some energy density to the universe and enabled galaxy formation to happen. And so in a really very real way, you can think of the fact that we are here as partially as a result of neutrinos. Neutrinos are also born in some of the most cataclysmic and violent processes that happen in the universe, supernovae. So here we've got a picture of a galaxy, and you can see where the top arrow is pointing is towards the center of that galaxy. And you can see how bright that center is, where all these stars are packed together in the center of this galaxy. If you look down to the lower left corner where the other arrow is pointing, that's a supernova that went off. It turns out it went off in 1994. And you'll notice right away that the light from the supernova rivals the amount of light being produced in the center of the galaxy. There's thousands and hundreds of thousands of stars and millions of stars in the center of that galaxy. Only one star produced that supernova. That's an incredible amount of energy that was released when that star blew up and died. As much energy that is in the visible light, that's only 1% of the total energy released in that supernova. The other 99% came in the form of neutrinos. So it spewed just all these neutrinos out into the universe. We can get a little closer to home too. Neutrinos are produced in the fusion reactions that happen inside of stars, like our sun. It turns out that there's 100 billion neutrinos that are produced in the fusion reactions in the sun that are going through your fingernail every second, day or night. Now, you might be thinking to yourself, wait a minute, how is that happening at night? The sun's on the other side of the Earth. Well, remember, neutrinos just don't care about matter. They will happily go through a light year of lead. So the little bit of rock that the Earth is really doesn't matter to them. And so the sun is producing all these neutrinos, so many such that 100 billion of them are going through your thumb every second, your thumbnail every second. And we can get even a little closer to home with the neutrino production. Bananas. It turns out that the average banana will emit about 1 million neutrinos every day, and that's just due to the radioactive decay of the potassium isotopes that naturally occur in the bananas. It's not like these bananas are somehow, they're somehow been altered or they're not organic or anything like that. It just turns out that there's naturally occurring potassium isotopes that will decay, and they will emit about 1 million neutrinos every day. So if you had a banana at some point today for breakfast, for lunch, for a snack, congratulations, you are emitting neutrinos as we speak. Now, that's all great. Those are great facts to know about neutrinos. But why are they interesting? Well, back in the 50s, 60s, 50s, 60s, we discovered a really interesting mystery that came along with the neutrinos. This, what you're looking at here, is a picture of a detector that was the first detector built to try to observe neutrinos coming from the sun. It was called the Homestake experiment, and it was put in a mine, a gold mine out in South Dakota. As I say, it was built to observe solar neutrinos, but they only saw a third of the neutrinos that they expected in this experiment. And so that, when you see something so different from what you expect as a scientist, you have a couple of options. One is that your expectations are just plain wrong. Two, that your detector isn't working the way you think it should be working. Or three, something else is going on that's really interesting. And they, so they checked their models of solar fusion, and they looked to see, and they could look at other predictions based on solar fusion models of like the energy output of the sun, seismic waves on the surface of the sun, everything panned out. So it looked like the sun was producing the number of neutrinos that they expected. They looked at their detector. There was nothing wrong with the detector. So what's possibly going on? Well, in a case of life being stranger than fiction, it turns out that the solar fusion models were right, but our understanding of the neutrino was just plain wrong. And what happens with neutrinos is that they do this really weird thing. They can change their type depending on how much energy the neutrino has and how far the neutrino has traveled since the point of its production. And so, for example, you can take the nu e, which is in the top left there, and after a certain amount of time, it might turn into a nu mu. And sometime later, that nu mu might turn into a nu tau. And this is really weird, because remember, I told you those are fundamental particles. And so why would they possibly be doing this? It's a bit like going into your kitchen again to get a banana for your breakfast or a snack or whatever. You walk towards your dining room table, and suddenly it's an apple. That's just completely out of the realm of what you would expect, and it's what neutrinos are doing. And it turns out the reason they can do this, it has to do with quantum mechanics, and we're not going to get into that, because the really important part of the story is the fact that they can do this. And before we get to the punchline with why that's important, let's take a little digression and talk about the history of the universe. Just a small one, 14 billion years. We'll get there. So in the early universe, at the point of the Big Bang, the universe was equal parts matter and antimatter. What happened is that it produced particles and antiparticles, and when those particles and antiparticles would come together, they would annihilate each other, and they'd turn into energy. That energy would eventually turn back into particles and antiparticles, and this was happily happening in the early universe until about 10 to the 5 seconds, which in the time of the early universe was all there ever was in the existence of time. But something happens at 10 to the minus 5 seconds. Something happens in that fraction of a second when the interactions of matter and antimatter go out of equilibrium. You no longer have the same number of matter particles as antimatter particles. And we can think of this in a slightly more schematic way of looking at it. So at the Big Bang, clear at the top of the slide there's about 1 billion and one particles of matter in the universe. There's about 1 billion and one particles of antimatter. This is just for illustrative purposes. There's way more particles than that. And then, a very short time later, 10 to the minus 5 seconds, suddenly we have about 1 billion and two particles of matter and only 1 billion particles of antimatter. Now remember, I told you that when matter and antimatter come together, they annihilate. And at some point, ever since then, we have an imbalance where we have matter, but no antimatter. So the good news is we won. We're here. The question is, why? Why did that happen? Well, you know, there has to be a difference between matter and antimatter to create that asymmetry and that imbalance. And that difference can't come from the quarks. Particle physicists have looked for it. And those quarks that I told you about at the beginning of this talk, they don't have enough of this asymmetry between matter and antimatter to actually cause that imbalance. So it has to come from somewhere else. And so a really good option would be the neutrinos, or the leptons, specifically the neutrinos. And so we would like to try to figure out if, in fact, neutrinos and antineutrinos do this transition from one to another in slightly different rates. Because if the nu E up top transitioning to a nu mu there is different from an anti-nu E on the bottom transitioning to an anti-nu mu, that can tell us something about this matter-antimatter asymmetry, and maybe it's big enough to explain why our universe is only made out of matter, and ultimately why we're here, which is a really cool thing to go look for. So how do you do that? Well, you need a plentiful source of neutrinos that you create, and thus you control their energy and how far the neutrinos are traveling. Because remember, I told you this process depends on how much energy a neutrino has and how far it's traveled. Turns out at Fermilab, which is just outside of Chicago, we can make 60 trillion neutrinos about every 2 seconds. And so check that. We've got a plentiful source of neutrinos, we control their energy, and we can point them in the direction that we want them to go to intersect our detectors. The other thing you need is a huge detector to catch the neutrinos and the antineutrinos and try to measure them. Now remember, I told you that neutrinos just don't care about matter, right? They just pass through everything. So how in the world do we actually detect neutrinos? The answer is we make a whole boatload of them. We throw them at something that is enormous, like the detector that I'm showing you the inside of it here, called DUNE, the Deep Underground Neutrino Experiment, which will use 40,000 tons of liquid argon located a mile underground to try to detect these neutrinos. And the hope is that we'll see a handful of interactions, a handful of neutrinos interacting on our detector every day. Out of those 60 trillion that we make every 2 seconds, day or night, we're going to see a handful every day. Now, the cool thing is that UW is providing critical components to this detector. We are making some of the fundamental pieces of what's going to enable us to record the neutrinos interacting in this detector. The slightly less cool or delayed gratification aspect of it is that we need at least 7 years of data to find a definitive answer, and it's going to take us another 7 years-ish to actually build the detector. So stay tuned. 14 years, we may have an answer for you. Thank you.
All right. Hi, everyone. My name is Tullia Dymarz, and I'm a professor in the math department. So yes, this is going to be a talk about math, but I promise you there will be no formulas. But what I am going to talk about is the size of collections of objects. So we usually call those sets in math. But you could, for example, look at this drum kit and say, that's a collection of objects, and then we could, try to see how many objects are in that collection, that drum kit. And I feel like I'm the only one who's really addressing the small, medium, and large in this, because everyone chose one of the topics, but I'm going to do all three. And so for the first topic, for small, right there, I'm going to talk about what you're probably most familiar with is finite collections of objects. So here's my first slide. So here I have two collections of objects. I have green hearts and red hearts. I don't know why I chose these particular collections. It's because my slides program had this available to me. And so instead of just looking at a single collection of objects, a single set, what I'm going to do is compare two different sets, so the green hearts and the red hearts. And I'm going to ask which collection of objects has more objects in it. Okay, so there's several ways to approach this problem. One way that you might do it is simply count how many objects one of them has and how many objects the other one has, and compare those two numbers. And then we see, okay, 2 is less than 3. So yes, the set on the left with the green hearts has fewer objects. Don't worry, it'll get a little harder soon. Here's another way that I actually recommend doing this. Instead of counting, you don't actually need to count. What you can do instead is match objects from one set to the other. So here I've matched the 2 green hearts with 2 of the red hearts, and I see in my set on the right I have a blue heart that's left over. And there's no other way I could possibly match these sets so that everybody has a partner. And so they just don't have the same size, these 2 sets, because I couldn't match every object in one with every object in the other. And in particular, that set on the right is bigger because it has an object that was unmatched. Okay, so that's all I'm going to say about finite sets. And if you were really hoping to learn about, I could also talk about big numbers, but I won't. But there's this really cool book that I got for my nieces, and I just wanted to tell you about it. It's written by a mathematician. It's called Really Big Numbers. So if you really want to think more about big numbers, I highly recommend this book. It might even be available on the internet for free. But let's move on to the harder topic here. And this is the medium-sized sets, medium-sized collections of objects. So I already said, small means finite. And so now we're moving into the realm of infinite. So probably the infinite set that you are most comfortable with is just the counting numbers, like 1, 2, 3, 4, 5, and you can keep going forever. Okay, those are called the natural numbers. Has anyone heard of Hilbert's Hotel? Has anyone stayed at Hilbert's Hotel? This is Hilbert's Hotel, not drawn by me, stolen from the internet. So Hilbert's Hotel has a room for every single number, counting number, 1, 2, 3, 4, 5. And so what happens is even when Hilbert's Hotel has no vacancy, so that means every room was matched with a person. So imagine that your collection of objects is the set of people who are staying at this hotel. Well, what if someone else comes along now, and they also want a room? And so at first glance, you're like, well, there are no rooms. But if your guests are polite enough and are okay to just move over to the room to the right, then this newcomer also gets a room. Okay, so I had a collection of objects, this set of people who was at the hotel, and I added one extra person, and still I was able to match them with a hotel room. Okay? So weird things happen when you get infinity, when you start comparing infinite sets. So an infinite set that is, all the natural numbers, if you just add like one other element to that set, it's still exactly the same size as the original one because you can still match them all up. Okay, here's some numbers. Okay. So these are 3 different sets here: natural numbers, even numbers, and integers. I'm guessing everyone is familiar with these sets of numbers. And you look at these now, and you see, well, even numbers compared to natural numbers, it looks like you're missing half of the numbers, right? Because you're missing all the odd ones. And definitely, you're missing half of the number. Like natural numbers are kind of like half of the integers. But my claim to you is that all of these sets actually have the same size. So let me show you. Now remember, how do you figure out if things have the same size? You just have to match them. Okay, so let's match them. Here you go. Natural numbers matched with even numbers. Every even number is matched with a natural number. I said there was no formulas, but I guess I'm saying, n goes to 2n. But still, not a formula, not a formula. Okay, here I matched, oh no, I wrote this wrong. I'm sorry, slide mistake. Those are not even numbers. Those are integers. Sorry, I am not used to making slides. Okay, So these are the numbers, if you remember my very first slide of the median section, these kind of sets are called countable. You're called countable if you can match, I'm gonna go back to this side so there's no error here. Okay, there we go. A set is called countable if you can match it with the natural numbers. Basically, so if you can count it, even if it's like, you know, going off to infinity. So that's what I'm calling countable. Okay, there we go. Oh, sorry, I did have the slide for this. Okay, so, or finite. Okay, if you stop after finitely many things, the mathematicians also call that countable. But for us, we're thinking about infinity, so that's countable. Okay, now comes the hard part. Uncountable. So my question to you is, can you imagine a collection of objects so big that you can't even count them? Okay, so here's another collection of numbers that you might have seen in school. This is actually the real number line. If you want to be fancy, you can call it the continuum. And every point on this line defines a number. So here I have 0 is right about there, 1/4, 0.25, that's right about there, and that's 1/3 over there. And of course, those are the only digits of pi I could remember, but that keeps going on forever. Yeah, I should have just found it on the internet and like pasted a giant picture there, but okay. Maybe some of you know pi to more digits than I do. So my claim to you is that actually these guys are not countable. And so what that means is I can't, you know, be like, okay, that's my first number, that's my second, that's my third, that's my fourth. I can't make a list that contains all of these numbers. Okay. And so I said there would be no formulas in this talk, but there is going to be a proof, which is almost more scary. And I'm not actually going to prove to you that all real numbers are uncountable. I'm actually going to pick a much easier set to work with. And this, I'm going to call it A, because mathematicians like calling their sets by capital letters. So that set is A. And it's going to be all numbers that look like 0 point and then either zeros or ones. And like any possible list of zeros or ones that you have, if that's what your number looks like, then you're in that set A. So you've just, you know, all the guys that look like 0 point, something with zeros and ones in it. So like 0.1 is in there, but so is 0.11111 forever, right? Okay. So here's I should have said theorem because that would be even fancier. So I claim that you just can't count these, and that means you can't write them in a list. And well, how do you know that you can't do that? Well, one thing mathematicians, if they're trying to show that you can't do something, they just go ahead and try to do it. Okay, so let's try to do it. So actually anybody could do this, right? Start writing down your list of, okay, obviously it would take a long time to actually write down that list because that list is still infinite. However, we can imagine us doing this for the rest of our life, writing down this list. And suppose we had such a list, and I claim to you, I'm trying to say, okay, I made this list, I put all the numbers in it, and I tell you that actually you didn't. Okay, no matter what list you try to make, it's impossible for it to contain all numbers, and I will find a number for you that is not in this list. So this is it's almost like a magic trick. This is how it works. So you take your list, and then you notice that some of those entries I have put a red block around. And so in the first entry in my list, I put a little red block in the first guy there past the decimal point. In the second, I put a red block on the second guy. In the third guy in the list, I put a red block on that should be along the third guy, yeah, fourth guy. And then here at the very end, I have n, so n stands for any natural number. I basically take the nth guy, and I consider that. And so now I'm going to create a new number. Okay, I guess that sort of looks like a formula. I didn't have to have the x equals there, but again, mathematicians like to say x equals something. They like things being x. Okay. So what I do is, if in the first number there was a 1, I now put a 0. So that's why my first entry is 0. And now I look at the second entry. In my second entry, there was also a 1, so I change it. And in my second entry here, I put a 0. And third entry, also 1, I put a 0. Fourth entry was a 0, so I put a 1 there. And then my dot, 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 my nth entry was a 1, so now it's a 0 inside x. And notice that x is not equal to the first guy, because they differ at least in the first element. It's not equal to the second guy, because they differ in the second element. Not equal to the, et cetera, et cetera. So it's actually, this guy is not equal to any guy in your list. So try as you might to list all of these guys, I can always find someone who's not in your list. Okay? And this is called Cantor's diagonalization argument. That's Cantor. I actually dug up the original paper where he's kind of discussing these ideas of there being sort of different sizes of infinity. For example, ones that you can count, which you can pair with the natural numbers, and other sets where you can't do that. Okay, I'm almost done here. So here's some questions for you guys. Are the rational numbers, so rational numbers are all the fractions out there. So like, what did I write here? 1/2, 2/3, 17/4. Consider the collection of all rational numbers. That's a lot of numbers. Are they countable? I'm not going to give you that answer yet. Actually, maybe I won't give it to you at all. You can think about it the rest of the time. And then ask me if you really want to know. And here's the other question. Does a square, so I'm imagining a solid square, have the same number of points in it as an interval? Or are there more? And or a cube, does it have the same number of points in it as the interval, that little straight line there? And apparently this is exactly a question that Cantor asked in a letter, was corresponding with someone, and they wrote something like, well, surely the square must have more points than the line. But then when they actually went to prove it, they proved that all of these guys have the same number of points. And his quote is, "I see it, but I don't believe it." So anyway, that's math for you. Here's another, I just love these books so much. This is about infinity. They're great for kids, but also adults like me even love them. If you want to know more about infinity, I'm not sure they do different kinds of infinities, but I think it's a cool book to think about infinity anyway. And I am done.
Okay, am I on? Good, hi, I'm Paul Stoy. I'm on the Faculty of Biological Systems Engineering. And one of the things that I work on in lab, and many colleagues here at the University of Wisconsin, of course, is carbon dioxide and global change. And for the talk today, I want to talk about how these small carbon dioxide molecules have big global consequences. And actually, the reason for that is the characteristics of those little tiny molecules. So here's carbon dioxide. Look at how happy it is. That's one black carbon with two red little oxygens. And from this, we should immediately see that we shouldn't trust exactly what we find on the internet because the oxygens will be a little bit larger than the carbon. But it's a friendly, happy molecule, right? And then when we're thinking about the molecule itself, well, there's some bonds, and they move around, okay? They do a little dance. They do a little dance, do a little dance, do a little dance, okay? And you're seeing a number flash up there as well. Okay, that number is going to emerge to become very important. Okay, so the structure of this carbon dioxide molecule is very, very important for the entire Earth system. And on the point of not believing everything that you find, and this is going to go a little bit slowly because of the computer here, is that there's actually a fourth dance, right? It kind of goes like that fourth dance a little bit, okay? All the different ways in which this carbon dioxide molecule can orient itself right, is unique, and it's actually really important. Right? And one of the reasons it's so important, okay, is that the thing that's exciting these molecules, right, the reason that they're doing that little dance is because of energy. Right? So those numbers that you've been seeing, those are different wavelengths of energy, right? Wavelengths that happen to be about the same as what the surface of the Earth is trying to emit back out into outer space. And so these molecules are absorbing some of that energy. So when we take a look at the entire greenhouse effect, right, this is fundamentally what it's about. Energy is coming in from the sun, most of it is passing right through the atmosphere. Okay, some of that energy is reflected by the atmosphere, some of it's reflected by the land surface, especially when it's icy or cold. And then once the surface is warm, it needs to emit some of that energy, or else it's just gonna keep on getting hotter and hotter and hotter. Okay, so it's emitting energy, and at those wavelengths, right, that's where that CO2 molecule is doing its little dance. Right, at particular wavelengths, it's doing different things. And that's the reason that energy isn't going back out into space, because those are the fundamentals of the greenhouse effect. So this infrared radiation is being absorbed by these molecules that are doing their dance, and then it's being re-emitted in all directions, including back to the surface. Right? This is why we have the temperature that we do. So what's been happening over the past many, many years is that, of course, carbon dioxide and other greenhouse gases, right, other gases that are absorbing infrared energy and emitting them in all directions, have been increasing. And so with a new report that came out a couple days ago, you're off the hook for not having noticed, because there's other things happening in the world right now. I didn't notice either, right? But this carbon dioxide levels at the highest value has been ever recorded in human history, 419 parts per million. Methane levels as well, right, are at their highest value ever. They've really been spiking lately. We don't know why. This has been a huge concern in global change science. We can't really figure out why methane is doing what it's doing. And also nitrous oxide, right, a particularly powerful greenhouse gas. We have higher values of these gases in the atmosphere than we ever had before. And of course, over time, right, all of these greenhouse gases matter, but the most important in terms of the energy that is being absorbed and trying to go back into space that is kept in the Earth system is due to carbon dioxide. Right? And so when we plot the global concentrations of carbon dioxide, back from once we had consistent records from the Mauna Loa Observatory in Hawaii from 1960 until really the present day, this is a couple days ago, you see a steady increase with a lot of really interesting oscillations, right? A lot of little ups and downs. What's happening here, right? What are these medium things that might be impacting the entire Earth? Okay, and as a consequence of that increase in carbon dioxide, of course, we have increasing planetary temperatures as well. So if we dive into that graph, right, dive into that figure of increasing carbon dioxide, you see a trend in black, and you also see a monthly pattern that can be really quite pronounced in red, with a peak that happens kind of in the spring, like about now, or late winter, and then a trough that's happening sort of in late summer, right? We have this oscillatory pattern. The reason for that pattern is photosynthesis. Okay, plants really love this carbon dioxide. They want to take it up. They are growing faster because there's more elevated CO2 on the planet. Okay, weeds are growing faster too. Poison ivy loves it. Okay, so that carbon is being taken away from the atmosphere, of course, by photosynthesis. And with this figure from NASA, you can see the rich global patterns of where photosynthesis is occurring. It's always occurring in the tropics, but there's dry and wet seasons in the tropics and monsoons and other things. Okay, and then in the temperate zone, right now it's winter, and you see nothing happening, for example, in North America. Oh, now summer again. Okay, summer is green, winter's going back to brown, and you see this pulse, and most of the land area, of course, is in the northern hemisphere. And it's that northern hemisphere drawdown that's causing the global atmospheric concentrations to decrease and reach their trough in late summer, early fall. But it's more than just that, right? Plants aren't just blindly taking up carbon dioxide, or else they'd just be growing into infinity. What's really happening is that plants and animals and microorganisms are using that carbon, right, for their life process, which means that they're respiring carbon back into the atmosphere. So there's a net flux. Photosynthesis takes it in, then all of the biological processes combined in the plant and the soil with microbes, all the different animals, fungi, okay, those are emitting it back out into space. And so what this figure is showing us from my colleague Marcus Reichstein is how that process is working. So when you see the land surface kind of sinking in as if there's a massive sort of, I don't know, earthquake or something, that is carbon being drawn down, kind of in the blue. Okay, that's the land surface taking up carbon dioxide. And every time it's in the red, right, that's a net efflux back to the atmosphere. So the land surface and ecosystems, of course, are playing this extremely dynamic role in the global carbon cycle and therefore the global climate system. And we're still trying to figure out a lot more about exactly how that works. Because this is just an outcome of models that use a lot of formulations as well as something called data assimilation to make the best estimate. Okay, but it's just an estimate, right? We'd still love to know more about the global carbon cycle. And so when we come back, right, to our home, when I was up this morning, heard the birds chirping, right, we know that spring is around the corner, even though it's going to be about 4 degrees tomorrow morning. Okay, spring is going to slowly happen. And I think I need to click this one again. What we know, right, is that we're going to eventually see things starting to get green. And then we'll eventually see the global carbon dioxide concentrations begin to go down again. So this figure is updated just for a couple days ago, and it shows that, right, actually a lot of the southeastern United States, leaves are emerging ahead of their typical schedule right now, but it's really droughty in California, even though they got a big, big dump of snow in December. It's some of the driest it's ever been across much of the western United States. Lo and behold, once again, okay, so we have a later than normal leaf out. And this phenology, how plants work seasonally, right, gets very important for understanding that seasonal pattern in global carbon dioxide concentration in the atmosphere. So this is the big question, right? We have our little molecule. We're going from small to big. And where it goes next gets to be very important for the entire planet. Is it going to stay in the atmosphere, like in the top? Is it going to go into some beautiful forest, perhaps stay there for a while? A different type of ecosystem? In that case, it's a desert. Is it going to go in the ocean? Right? Maybe be emitted quickly, or maybe be sequestered for a long time? Or is it eventually going to find its way into rocks, like that lower figure, right? And probably stay there for quite some time? Right? The eventual path that our friendly carbon dioxide molecule takes is extremely important for understanding our climate system, right? And for the future of our planet. So that's all that I had for everybody today, and thanks for your time.
So, hi, I'm Raymond Deneckere, and I'm professor of economics at UW here. My area of specialization is game theory and industrial organization. And what I would like to talk to you about, without pictures, is a topic that has attracted quite a large amount of research over the last 25 years in economics, and that's the subject of auctions. And most everybody is familiar with auctions in some ways. You may have seen storage auctions, maybe even watched a TV program called Storage Wars, or you may have seen used or car or antique car auctions, or maybe you have bought collectibles on eBay, or maybe you saw art auctions in Sotheby's, or maybe you went to a silent auction in a charity. While these auctions are certainly entertaining, otherwise we wouldn't have TV programs about them, and certainly intriguing, it may seem to many people that it's a rather arcane subject area, that the auctions have gotten 2 Nobel Prizes in economics over the last 25 years. One by Vickery in 1996, and another one by 2 Stanford economists, Paul Milgram and Bob Wilson in 2020. So apparently there's more to these little auctions than meets the eye. And there's a number of ways in which one could, of course, measure size or impact of auctions. And I'll start with the simplest possible one, and that is, let's just look at auction activity in the economy. And there, when we look at this bigger picture, there's a lot of volume of transactions that are actually occurring through auctions. The stock exchange works through auctions. This is what's called a double auction, where buyers and sellers compete at the same place. Government auctions to privatize or to sell off assets, such as timber, or spectrum auctions, or offshore oil leases, or emissions permits, or even treasury bills. So a lot of things are sold through auctions, and it's not just the government, but there's that sells off assets, but the local, state, and federal governments allocate contracts on the basis of auctions, and businesses also allocate contract on the basis of auctions, and also buy some of their inputs through auctions. So the whole volume of auctions that gets used in the economy is indeed quite large. It's just not quite as visible to the average person. But economists, like mathematicians, like to take a more abstract view. They try to extract the essential ingredients in order to be able to make predictions about things that are much less obvious as applications. That's the whole process of science. And so what I would like to do today, in going from the seemingly arcane little auctions to a bigger picture, is to tell you a little bit about applications of what we have learned in auctions over the last 25 years to a variety of different areas where the applications might not seem nearly as obvious. So let me. So I have 3 things in mind to talk about. One of them is a legal context, the design of laws. How I want to claim that auctions have something useful to say about this topic. The other one is more political economy or sociology. And the third one will be drawn from the area of biology, which seemingly are all far away from economics. So Let me start. With the legal applications. There's been lots of complaints that the United States is a litigating country, that we spend way too much money on suing each other. And politicians have taken note of this. Now, the American system, the American legal system, each party in a dispute is responsible for their own legal expenses. And there are different systems. For example, in Britain, the loser has to pay both her legal expenses and that of the winner. And Dan Quayle, who was vice president under H.W. Bush, proposed a different system, a different legal system, in which the loser would have to pay not only would have to compensate the winner by the amount that the loser spent on resources. So the idea that Dan Quayle had was, well, for every dollar that you spend extra on litigation, you might end up paying twice as much. And so the hope was that this would deter people from litigating. And there's a famous result in auction theory called the revenue equivalence theorem that basically pointed out that Quayle's system and the current system will have exactly the same amount of litigation. And so one might ask, well, what's wrong with Quayle's reasoning? It seemed pretty convincing. And the answer is that, well, if you go to Quayle's system, then the value of winning is higher because you will be compensated for your legal expenses if you win. And so this makes people want to spend more. And it turns out, on average, these two effects exactly balance each other out. So here we have an area of applications that the British system, it turns out, is even worse. You might recall in the British system, the loser has to pay the expenses of the winner, so he might end up paying even more. And the net effect of all of that is that there's even more litigation expenses in such a system than in the American system. So here is auction theory giving some insight into how can we design legal policies. My second area of application is called renticipation. And what renticipation is about is it's a situation in which many individuals spend resources or effort to win a prize, to win some kind of a reward. And so, for example, you might think of winning a promotion. Okay, there's only somebody will get promoted, but not everybody can get promoted, but we all compete for it, or we all compete for a job. And there's very many examples of this. R&D competition. Several companies are spending R&D, but only one of them is really going to win and essentially capture the entire market. So we don't usually think of these things as auctions, but they have the same features because firms spend money on R&D, that's like bidding, and only one runs away with the prize. So they really have the same features as auctions. And another very important application here is that of lobbying. I just want to, I looked up some numbers. In 2012, the expenses for the presidential election were $2.6 billion. In 2016, that had grown to $6.8 billion. And in 2020, the latest one, it was $10.4 billion. Sorry, $14.4 billion. So these are huge sums of money. And what political economists are worried about is that a lot of these expenses are not socially productive. That is, the participants compete, and in the process of trying to grabbing the wealth, they actually do not create any new wealth, they just destroy wealth. So that, so the worry is that rent seeking causes harm, it causes real losses to society. So if you take it into the context of lobbying, what that means is that all the expenses that go into lobbying, the people that say do the TV advertising, they could be producing something else. Okay. But now all they do is what one could basically just think of as some form of persuasion, okay, which does not really create any information. Okay, if it created information, it might have extra social value, but typically it is just, it's kind of like advertising. Okay, and so what auction theory shines lights on is what amount of these expenses really are social waste. And what we have found is that the more candidates there are, the more competition there is for grabbing this big prize, the higher the total amount of expenses combined over all the individuals that are competing will be, and that if that number is large enough, their total expenses will be so high as to be exactly equal to the social value of the prize. So they are spending so much that on that, nothing is being contributed to society. Now let me spend one more example here. This is from biology. This John Maynard Smith came up with a model where there's a conflict between animals. They are fighting for prey, or they are fighting for a mate. And in this process, of course, they fight and they spend resources. Resources because they spend energy, okay? And energy is important for animal survival. And they might get injured. So it's again as if they are bidding. They are spending real resources, and only one of them wins the prize. So it is very much like an auction, even though there is nobody that's collecting the revenue from this auction. Okay. And in a broader context, there's many social examples. For example, a strike, which is very much like two animals fighting. We have labor versus management, and it's costly for both sides to fight, and the one who fights the longest wins. And we have seen strikes that sometimes last up to 2.5 years, like the Pittston strike. So these are very, very strong. These are fights that last for a very long time. Technology battles, battles to drive competitors out of the market. This is called predation. So there's lots of examples in the economics world that kind of are very similar to the biological competition. And what I want to end up with here is a feature of these auctions, which is really very, very strange, and that is sometimes these battles can go on for they're called war of attrition, by the way, and these battles can go on for so long that the animals fight for longer than the value of the prey, so that and of course they don't expect this to happen. They expect that some of the time they will not have to, but once they have fought very long, they have to. This is an economics lesson. Whatever you spent before, that's water under the bridge. We call this sunk cost. You should not take it into account. You should be forward-looking in your fight and see, if I spend a little bit more now, what extra am I going to get versus what will it cost me? And that calculus can be positive, and so we can see really very protective. If two very strong animals or two very strong-willed management and labor fight with each other, we can see very protracted fights that spend what each side is spending more than it was worth it to them. So we again an important application of auctions. All right, I'll leave it at that. Thank you very much.
I'd like to thank our brilliant presenters. It is really the presenters who make SoundWaves a successful series. And always they peel back the onion and reveal parts of our everyday experience that we never even thought to ask questions about. For instance, I never thought about an auction before in my life, and it turns out that a lot of what we do is a form of auctions. Just to use one example. I also never thought of the drum set as a set, even though set is right there in it, and it is a collection of instruments. And it is a collection of instruments that are small, medium, and large, which is how I managed to kind of shoehorn that into our theme. And I'm joined here on the stage by my colleague Matthew Endres, who teaches drum set at our School of Music, where I teach French horn. And we're going to talk to you a little bit about drums and the drum set and have some demonstrations and show you how this collection of instruments works. Talk a little bit about the history of the drums. And then Matt's going to do a little drumming for you. So drums are very old. They've found drums that are older than 5,000 years old. And basically what a drum consists of is a stretched skin over a frame. And as you probably know, all sound comes from vibration. Brian, you can correct all these ideas later. But all sound comes from vibration, and in order to have this vibration, you have to have some sort of resistance. So when you hit a drum, there's this skin that's stretched tight, it's hit by a stick, we get resistance, vibration, it creates a sound. In the case of the drums, it often creates a very loud sound, which makes it excellent for communication, also for celebration. You can also hit a stick on a log, which is a kind of a unmanufactured drum. So it's kind of a no-brainer to think how did people come up with this idea of drums? And there are, in fact, a whole bunch of drums here in a drum set. So we just take it for granted. Oh yeah, drum set. He plays a drum set. Oh yeah, Matt, he's a great drummer. He plays a drum set. But why is there a drum set? There wasn't always a drum set. In fact, it used to be that in a concert or a show, you'd have somebody playing a bass drum, somebody playing maybe a snare drum, somebody playing the cymbals. You'd have a lot of people playing these percussion instruments. There is a long and distinguished history of innovation putting musicians out of business, and the drum set is exactly such an example. So even though people were starting to play drum sets as early as around the 1860s, just collection of instruments. Of course, there's only two hands on a typical human body. And we want drum sets to have more than two drums. So pedals were invented where you could push a pedal and make a drum go with a pedal, or make a cymbal go with a pedal. But the economics were such that on Broadway, for instance, we're now turning around the turn of the century into the 20th century. Broadway was a very popular form of entertainment. Of course, there was no television, and people went to shows. And in Broadway, the pits are small, and having 6 percussionists takes up a lot of room, and it's expensive. And so if you could have one person play 2 of the percussion instruments, that's a lot cheaper. 3 of them, that's a lot cheaper. 4 of them, that's cheaper still, and so on. And there was economic pressure to develop this instrument, the drum set, and make it work. Now, it turns out that in early silent movies, there would be often an orchestra playing, and in vaudeville shows, there would be an orchestra playing. But especially in the silent movies, where there was no sound, of course, coming from the screen, it was very desirable to have sound effects if a door slammed, or if a window creaked, or whatever. You would want a sound effect there to represent that. And so, in essence, the drum set players became Foley artists. So they were creating the sounds that were viewed on the screen, and they had a collection of stuff that they could make different sounds with. It was really a collection of contraptions. And they brought these contraptions, they had them at work, and they could create sound effects with them. And so that word contraption eventually got shortened to trap. And so you had your kit, which had all of your trap in. It was called a trap kit. And so still today, people often call the drum set the trap kit. And even though it's much less contraption based now, and drummers are no longer called on to do such things. Now, once we had the drum set become standard, as ragtime became a popular music form, drum beats became, they really could create the feel of ragtime. Can you do a little bit of something that feels a little bit like ragtime? I'll hold your mic.
Oh, okay. Could I say something quick? I'll play this in a there's a difference between ragtime and a rag approach. Rag is like a compositional or a way of performing a piece of music. You can play any piece of music as a rag. So I can approach the drum set in a way where it's more of a heavily syncopated sort of approach, which would be meaning or leaning towards this idea of rag. So that's kind of what I'll be doing. kind of like a New Orleans emphasized street beat that you would hear from what you would hear from a New Orleans brass band like the Excelsior Brass Band or the Onward Brass Band, something like this, something heavily syncopated.
Thank you. So as music continued to evolve, these different kinds of drum beats, which really drove the feeling, or the word we use now, the groove of particular styles of music, became the mission of the drummer. Until now, we have drummers who have these sort of complicated but sort of simple drum kits and can play all kinds of styles of music, and we're going to get into some of those. I thought the first thing that we should do, we've got some large instruments, some mediums, and small. I wanted to just take you through, with Matt's help, all of the instruments in at least this iteration of the drum set, bearing in mind that it can be much bigger, it can be much smaller and simpler. For any of you that know, for instance, the band Rush, there's just toms galore. I don't know how many toms. Neil Peart played. Yeah, we don't know, but you can really build up the drum set. You can put cymbals overhead. You can play cowbells. So we have, I think, a pretty standard setup here. So can you kind of take us through the drums first, from big to small,
Sure.
and then the cymbals?
Yeah. So what I have right here in front of me is the snare drum, which would be the sound that all sort of American popular music, our emphasis is on beats 2 and 4, or what you would typically clap to at a concert while you're listening to a tune or a composition. So this is the sound that you would be hearing on those beats 2 and 4, or what you would clap to, the snare drum, and where it actually gets its name is it has a very, very distinctive sound, a sort of rattling, vibrating sort of sound, which is produced by snare strands on the bottom of the head under here. So if I were to show
let's hold that up.
There you go. So they are metal strands which vibrate after you strike the drum, and which makes them give that sort of tone quality to the drum. And originally they were made out of guts from cows or goats or something like that were dried and stretched to string along the bottom of the heads, and which also for some early stringed instruments as well were made out of guts to have that kind of sound. But that produced a much drier, darker sound. But here, a more brighter sort of sound because of the metal strands. So that's a snare drum.
Matt, all of your drums have a skin above that you hit and a skin below as well that you don't hit. Why is that?
Well, by having a top head and a bottom head with different tensions, they create different sorts of overtones. And so several, or at least 2 different pitches that are being played at the same time, unless you tune them both to the same pitch, which I like to do on my drums, sometimes to have a deeper, more, what they would call a more fusion-y depth sort of sound on these drums, like the tom drums. You would take the bottom head and you would pitch it lower than the top head, meaning that the tension on the bottom head is more loose than it is on the top head, which makes it more of a sort of sound. Traditionally, that's why there's 2 heads on there. Sometimes you'll come across drums that do not have 2 heads. Of course, there'll be a head on the top so you can create sound, but on the bottom, it might be headless to just create a different sort of tone quality. It's a little bit more brash of a sound. It's more resonant, but has less overtones than you would have if you had 2 heads.
So let's move on to the toms as we get bigger.
Yeah, so the toms here, this is considered a rack tom or a high tom, usually because it's on a rack, or traditionally it was mounted originally on a rack, but now due to the development of hardware for drums, we have this arm sticking out of the bass drum and holding it. So this is considered a high tom or a rack tom. And you could pitch them to different pitches and higher and lower frequencies, depending on how tight you want to, of course, have the tension of the head. So traditionally, now we're moving down to a little bit lower of a sound. However, it is a smaller drum than the snare drum, but the tone quality and the pitches are different because this head on the larger drum is tighter than the head on the smaller drum, the tom. But traditionally, that's going to be a lower pitched drum. Moving on down here is another tom drum, traditionally called a floor tom, because it stands on the floor and it's not being hoisted up by a rack, which is pitched and tuned even lower than the other toms. I only play with 2 toms because I play often, and I learned very quickly that less is more for myself, and then I don't have to make as many trips out to my vehicle. So that's traditionally why I do. But I feel that if I'm going to make any music at all, I should be able to make as much music as I possibly can with the least amount of equipment that I can. So traditionally, the floor tom, or as we move from left to right, if you're a right-handed drummer, which majority of drummers are, the pitch and the sizes of the toms will largen or get larger. Largen, I don't know if that's really a word, but get larger. And then the pitch traditionally will get lower and deeper. So high tom, floor tom. Down here, the bass drum, which traditionally is the lowest pitched drum within a drum set. And traditionally is also mostly the largest drum. And do you want me to get into the roles of them, or is that something that?
Yes, let's do that.
Okay, so traditionally the bass drum will, if you're playing in a group or you're listening to a band or whatever, and if you could make any sort of parallels with another instrument with this bass drum, I would probably make parallels with the actual bass player, a bass guitar. Stylistically, if I'm playing like a funk composition or a funk tune, I might want to focus on what is the bass player playing? What kind of rhythmic bass line are they playing? Rhythmically, not pitch-wise necessarily, but rhythmically. And I might want to mimic that. Out of all these instruments here, I would probably want to mimic it with my bass drum so I could kind of accentuate the rhythmic aspect of what the bass player is playing by playing my lowest and deepest timbre of instrument here.
And you're playing that with a pedal.
Yes.
Can you show, is it possible, is it easy to take that off and show people?
Yeah, absolutely. So what we have here is basically a chain drive. You could grab it. A chain drive pedal, which is there's a tension that's made by a spring. Obviously, the higher the tension, the quicker the pedal will actually, after you release it, will come back. Everyone's kind of different with the kind of tensions that they like. Some people like not much tension at all. I kind of like a medium tension. So by pressing down, it obviously strikes the bass drum and it comes back automatically. So I don't need to pull it back manually. Anyway, so this is played with the pedal, and obviously the other drums will be played with sticks or brushes or whatever other sort of utensil I have.
So before we get into the function of the other drums, let's talk about cymbals a little bit. Cymbals made out of metal, of course, and the cymbals originally made in Turkey, and the best ones still made in Turkey. And so I see that you have one here, and then a little sandwich right here. So let's go from high to low.
Okay, so we'll start with the hi-hats here, which are cymbals. There just happen to be 2 cymbals that are basically pressed together by this mechanism called a hi-hat stand, which inside of here is a spring, a tension that kind of how the bass drum works. There is a spring inside where you push down. If I were to let go of the pedal of the hi-hat, they come back up automatically. So the bottom cymbal, or the bottom hat, what they're often called, is stationary, where the top hi-hat is held on by something that's called a clutch, which basically is a mechanism with a hole in there, and then there's basically a screw, a wing screw that you tighten on this basically a metal shaft right here, and you can do it at all different heights. Some people do it. Thank you. Some people do it. If I were to, you can adjust the height of the hi-hat, the top cymbal, depending on what kind of sound you'd like. I might want, if I were to have a bigger gap between the bottom hi-hat or the bottom hat and the top hat, this is going to be much more of a brash sort of sound. Where when I'm traveling less distance by having obviously a smaller distance between the top and the bottom hat, it's going to be a little bit more subdued, and you kind of have some more control over it. So hi-hat, traditionally, some of the smaller cymbals and controlled by the foot, the left foot, and also oftentimes played with the foot or, of course, with a stick. And then moving along over here, these are both called ride cymbals, and ride cymbals traditionally are larger because you would utilize them sort of with the right or left hand, traditionally how you would with the hi-hat, where you're playing a consistent pattern. However, these are special ones where they're actually extremely, extremely thin. You see, I can actually bend it quite a bit, and traditionally, most cymbals played are not this thin. They're actually quite thick, and I like to call manhole covers because they sound like them. And I really don't think that the sound is very appealing. So this, I can get many different pitches and tones and overtones. So I can use these as rides while I'm playing a groove, or I can actually crash it, which is the role of what would be called a crash cymbal, which is traditionally smaller, and it's mostly an effect cymbal that you would play, and you would just hit once at the end of a phrase or at the beginning of a groove or at the end of a drum fill to kind of define the ending of something or the beginning of something. So yeah, I can utilize these cymbals because they're so thin as rides and also crashes. So that's what we have here, and I will add right here in the middle, we have a raised part in the middle of the cymbal, which is called the bell, which has an entirely different tone quality than the body of the cymbal. A lot of times you can utilize the bell in different styles of music, oftentimes Latin influenced music, which will give it a different timbre and give it a different effect, so you can get many different sound qualities out of just this one instrument alone.
So before we start putting together these collections of instruments, you hit it now, you have drumsticks, they have a thin end and a thick end, but maybe you can talk about that a little, and then the other things that you can use to strike the drums and cymbals with.
Yeah, so traditionally a drumstick has a tapered tip or a tapered end that usually is where the tip of it is called a tip, of course. And there's many different shapes of the tip, so that is called a barrel tip. It resembles that of a barrel. And some other tips are called like just beaded tips, which is like just a circular end. Other ones called acorn tips, which you can imagine what that would look like. And it resembles, they all have different sounds to them. I enjoy the barrel tip because I enjoy dark, woody sounds. And that's the kind of sound that a barrel tip resembles. If I were to play an acorn tip, obviously there's a point and then it would come to an edge and then it would round off. So there's less of a surface area that's striking the cymbal or the snare drum, so it's going to sound a little brighter, a little thinner. But I like dark, fat, round sounds, and that's what a barrel tip produces. So the stick, then the bottom end, of course, is traditionally what you hold on with, but you can get many different sounds out of just the stick here alone. So if I were to go and then play with the bottom end, you get more of a washier, less defined sound, but more of a broader sound. So those are drumsticks. Of course, there's many other things you could strike the instrument with. Oftentimes played in jazz is the brushes, or what originally was called actually the fly swatter. Yeah, take it. Which kind of resembles a fly swatter, but that was the original name of the brushes, which of course creates an entirely different kind of sound. So, sort of like, and they're basically just wire strands. And of course, now we're going in the arena of attacking these instruments in a different way. Instead of just striking it, now you can get these different sort of swoosh sounds, where it's common if you're playing, well, traditionally you would do it more so in jazz, I suppose, if you're going to play a groove, which I can demonstrate later, I guess. And so now you have a different tone quality with brushes. Or, of course, mallets, which is underneath, which is really is really a drumstick, which would have a larger tip and then wrapped with felt and then wrapped with cotton, which is going to give you the more of a hollow sort of less defined attack sound. Also on cymbals, you can do things that are called cymbal swells. So you can crescendo, decrescendo, get louder, get softer, and create different effects with these. And then the last thing that I have up here is what are called lightning rods, which are essentially basically pieces of just sticks, tiny little spindles in a way of wood, which create an entirely different sort of sound on the drums and cymbals when you tack it. You can kind of lay into it a little bit more, but it's not going to be quite as loud. So I'll strike that drum at this height with the lightning rod, and now at the same height with the stick. Obviously much louder, the same distance being traveled, but they're lighter, and you can it creates a different tone quality, and you can kind of lay in and play deeper into the drums and cymbals without being overbearing in volume.
So you're talking about sort of painting with colors, tone colors, and you're talking about phrasing, bringing a band to the end of a phrase or to the beginning of a new phrase. So basically you're like, you're almost the punctuation in the sentence that a band is saying.
Yeah, that's a good way of putting it. Yeah.
Okay, so let's see how things are put together to make a beat. Just a very, very simple kind of a beat in some style of your choosing.
Okay. Since I brought the brushes up, I will play a sort of medium swing groove utilizing the brushes, and then I can do the same sort of thing with what it would sound like with sticks.
Can you direct people's listening with the different instruments?
Yeah, so I will be mostly entirely producing this swing pattern on the snare drum, and then the hi-hat, which I'll play with my left foot, will be played on what's called beats 2 and 4. So every time I hit the hi-hat, the first time I hit it will be beat 2, second time will be beat 4, and then 2 and 4 and 2 and 4, and then the swing pattern will be produced with the brushes moving at a horizontal and vertical motion to get a swish sound and a attack sound to create the swing pattern. So I was embellishing somewhat some of the rhythmic things that I was playing. But another thing, so I could just play a sort of basic rock sort of groove.
Tell about how it's going to be built.
So what I'll be doing is with the bass drum, I'll be playing a sort of bass drum variation, which you'll hear. It'll be the lower pitch drum. I'll be emphasizing with the snare drum on beats 2 and 4, what you traditionally would be clapping on if you were clapping to a tune. And I might also embellish it somewhat because I like to improvise, so I don't really know what's going to happen. And then I will that'll be played with my left hand. With my right hand, I'll be utilizing the role of what the hi-hat and the ride cymbal role will be. When I say ride cymbal, it's something that's played consistently, and you'll kind of get a taste of what that right hand roll is by playing a consistent pattern with the right hand.
So all 4 limbs are doing different things.
Entirely different things, yes. So
don't try this at home.
Yeah, look out. So those were 2 different groove examples.
Can you take us to another country?
Yes, let's go to Brazil, and I will play. I'll play what's known as a well, this is sort of an Americanized version of the groove, because traditionally in Brazil, if you were to play a samba, it would not be played on a drum set. It would be played with a number of different drummers playing different, basically different drums at one time to create one groove. But what I'm kind of doing is consolidating it into me playing the entirety of the groove. So a samba, which is really the music of Brazil, consists of what I'll call, with the bass drum or my right foot, a heartbeat pattern, which is 1, 2, and 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Hi-hat beats 2 and 4. 1, 2, 3, 4. 1, 2, 3, 4. Adding the bass drum. The right hand, doing the role of what it usually does on the ride cymbal, is riding and playing a consistent pattern, which is usually consists of combinations of quarter notes and eighth notes, and sometimes utilizing the bell, which I'll actually do here now when I'm playing on beats 1 and 3. I'll emphasize the bell. 1 and 3 will be on the bell, 2 and 4 will be on the body of the cymbal. And then the left hand will be a sort of a very syncopated or a rhythmically dense, improvised pattern that I'll play on the snare drum, where I don't strike the head of the snare. I actually play with the fat end of the stick, and the tip of the stick I will press down on the drum head, and then I'll raise it, and then I'll basically slam the body of the stick down, and this will hit the rim of the drum, which creates this sound. So this is a samba groove.
Just a confession that, yeah, let's hear it. This is not the first time we've done this kind of thing together, where he shows how to build a groove, and it's just amazing to me every single time he does it, that just a couple of instruments together and you're transported to the beaches of Rio, or, you know, to the jazz clubs of southern Mississippi. It's just amazing the amount of atmosphere that can be created by these different drumming patterns. I imagine it takes a young drummer quite a while to get the control to do this kind of thing, and to stay in time.
Yeah, definitely. Yeah, it's something that, you know, it's a very physically demanding sort of instrument, and like, you know, really every instrument is demanding in its own way. But the four-way coordinative comping and the four-way independence that's happening here between your legs and your arms, and on top of that, secondary independence on these limbs, like your fingers, all doing entirely different things, and your shoulders and your pectoral muscles, and to play it in a right way. So many people think that you know, to play a drum or whatever, it's bashy. You hit it, and it's you're supposed to hit it loud and brash. But this is a very melodic instrument, and its best tone quality that it can create is one when somebody plays it in a very relaxed, rebound-y-ish sort of way. Playing through the instrument and not heavy and loud, but just relaxed. And that's when it creates its best actual tone quality.
Could you do one more? Could you take us to Africa with something with kind of an African feel?
Yeah, definitely. So I'll play there's many different bell patterns that are played in Africa. This specific pattern is called the Bembe pattern, which is actually where this idea of the purely American music of jazz and this idea of swing actually came from this African bell pattern. So the pattern is ga ga gi ga 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 da da di di da 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 di di da da. And that's what I'm going to play on the bell of the ride cymbal. I will emphasize the hi-hat playing on every beat. So this is your pulse, and I'll be playing the hi-hat on every beat. And then I will then move around between the cross-stick pattern that I did with the samba, this sort of sound, and then moving around between a syncopated idea between the toms. And the bass drum will emphasize basically just the first beat of every measure, which there will be 4 beats in every measure. So this is the Bembe groove.
And that word syncopated, which you've used a couple times, refers to hits that come off of the beat rather than on the beat, correct?
Yep. So basically, playing in all the other areas of the beat. So instead of just right at the beginning of beats 1, 2, 3, 4, but all those other little spaces in between beats 1 and 2, and between 2 and 3, and things like that. So yeah, that's what I'm referencing when I say syncopation, which creates more of a dense sort of rhythmic feel. Thank you. So another very active sort of groove that's happening with each limb doing entirely different things.
This is great. I think probably everybody's ready to hear you do some playing.
Okay.
So yeah, okay. So I think Matt's just gonna make stuff up. It's gonna be completely improvised.
Pretty much,
is
yeah.
my guess. And why don't you go on for as long as it needs to go on, and that'll be our wrap up for the evening. So thanks so much for coming. Thank you for the AV crew that's making all of this work, and to Shauna Baranchik, who makes all the details happen, and to Discovery for sponsoring SoundWaves. And yeah, okay, so here comes some drums.
All right, thank you.
Thank you. Thank you so much for coming. Thank you, presenters. Come talk to us if you have questions.